Welcome, class. This is week 7, and we will be discussing linear regression. As we discussed before, we have learned the slope-intercept form of the equation of a line to be y equal mx plus b. Up until this point, the only tools that you've been given to solve this equation is an x and a y on our Cartesian coordinate system. If you give me an x, you can solve for y. Therefore, we're going to teach you how to undo it, because if we look at this equation, we can see that this equation can be used as a prediction model, where if we're given the value for x, we can determine the value for y. Therefore, y is dependent on x. So, for example, let's look at a dinner party example. If we're given the cost to rent the dining hall, and that's with all the amenities, to be $500, and the cost per person for the dinner is $25, how would we model this situation so that we can determine what the total cost for the dinner party is given this information? So we write an equation that models the cost of the dinner. So we have the total cost is equal to $25 times the number of people plus 500. And that makes a lot of sense, because you told me how many people that will be coming to the dinner party, and I can give you the cost, because I have to add the cost of renting a dining hall, which is $500. Now, if we let y equal the total cost and x equal the number of people, we end up with the equation y is equal to 25 plus 500, which is in line with our slope-intercept form of the equation, where our slope is 25 and our intercept is 500. Now give me a value for, tell me the number of people, that is, give me a value for x, and I can tell you how much it's going to cost. As stated before, to start this process, we're going to have what we call a scatter diagram. A scatter diagram is where we take values of x and values of y, apply it against each other. We call the x variable the explanatory variable, or we also call it the independent variable, because x changes, then y responds. So if I can explain x, then my y will respond accordingly. So let's look at an example where we have a pair of data, and we have the phosphorus concentration at an inlet and the phosphorus concentration at an outlet. And we have the information, we have the x and y data. And we want to take this data and plot it. So using our Excel tool, where x is the inlet and y is the outlet, we get our scatter plot. And with our scatter plot, we can use this information to draw our trend line. We'll see this later in our examples. So we want to look at linear correlation. The linear correlation is the trend that the points seem to follow a straight line segment. And if we can identify what that line segment is, we can use that information as a prediction model for x and y. Give me x, I'll tell you what y is. So we have different types of correlation. We have linear correlation, which is straight line correlation. And we also have some instances where we have nonlinear correlation. And we also can model those situations, but that is not within the scope of this course. Also, we have situations where we have no correlations. In other words, we can look at two different variables. In other words, we can look at rolling a die and pulling a card out of the deck. And we know that the number that we get when we roll a die has no effect on what card we get when we pull a card from the deck. So in this case, we have no correlation. When we look at our points, and our points are closer to a straight line, we know that we have a high linear correlation. And then as they begin to separate from the line, we get to a moderate linear correlation. And then as they continue to separate from the line, we get to a low linear correlation. And at some point, if all the points are on the line, if the equation is modeled exactly, then we have a perfect linear correlation. Well, what two things can happen? Well, we can have a positive linear correlation where x increases and y increases. So as the value of x moves to the right, which is our positive direction, the values of y move up, which is our positive direction. So we have a positive linear correlation. We can also have a negative linear correlation, which is not bad. It's not a bad thing because there are actually some situations out there that model negative linear correlation. For example, if I had an all-you-can-eat restaurant, the more people that comes in to the restaurant, my costs will go down because I have more people paying and eating the food, and it costs less. So as I move to the right, as the number of people come into my all-you-can-eat restaurant, my cost goes down. And that can be modeled in this situation. And we'll see an example later on. And then we get to the point where the dots are all over the place. And when the dots are all over the place, we have little or no linear correlation. We can measure this correlation, and we can ask ourselves questions. Can we find a relationship between x and y? And how strong is this relationship? So we want to know if we have a strong relationship. So we should be able to determine quantitatively if I have a strong relationship. Correlation coefficient is what is used to determine the strength of a linear relationship between two variables. Another name for the correlation coefficient is the Pearson product moment correlation coefficient. And this value lies between -1 and +1. With 1, when r is equal to 1, I have perfect positive correlation. When r is equal to -1, I have perfect negative correlation. So being at +1 or -1 is a good thing. Now, where does it go bad? When r is 0 or close to 0, I have no linear correlation. There's no linear correlation. And so the two variables do not correlate, and we can't use the prediction model to predict our variables. Positive values of r implies a positive linear relationship, inferring that as x increases, y increases. And a negative value of r implies that as x increases, y increases. And again, as we stated before, the closer I get to -1 or +1, the better the line describes the relationship between the two variables. And if I swap the two variables around, in other words, if I change my x and y value, the correlation coefficient will not change. I'll say that again. If I swap my x and y variables, the correlation will not change. The correlation coefficient will not change. In other words, I'm saying the same thing here. As long as I have the paired values, then when I compute the correlation coefficient, it will not change. Below you see the formula for computing the values of r. And that's a very, very strenuous formula because we have to lay out our information in Excel spreadsheet and compute these values. Well, we're not going to do that. We're going to let Excel do the heavy lifting for us and help us determine our correlation coefficient. As I said, computing the correlation coefficient, you have to lay everything out. And here's an example that you can view at your leisure, showing you how it is laid out. So again, when we look at the value of r, the closer it is to 1 or the closer it is to -1, then we consider that we have a strong positive correlation between the variables x and y. And just another example, of course, as we talk throughout the class, r represents a sample correlation coefficient because it is a sample, whereas p, the Greek letter rho, represents the population correlation coefficient. So we talked about correlation coefficient measuring the strength of the relationship between two variables. A strong correlation does not necessarily imply cause and effect. There could be a lot of variables out there lingering. The first thing, or the first test that any situation that you're given with two variables, identifying one as a independent variable and the other as a dependent variable, the first test that you have to pass is what we call the common sense test. In other words, does it make common sense for us to look at the two variables in the context in which we need to compare them? For example, it makes a lot of sense to compare the number of people that come into an all-you-can-eat restaurant with the cost that the restaurant is incurring for those patrons. On the other side of the coin, we would not want to look at average daily price of eggs in China and compare them with the amount of rainfall that occurs on a daily basis in the area in which we live in. Those two variables, the price of eggs in China and the amount of rainfall in, let's say, Washington, D.C., does not correlate. These two variables do not make sense to correlate. So we have to ask that question, does it pass the common sense test? And in your readings and in your daily travels, you'll see a lot of people trying to take two variables and tell you that they correlate, when in actuality it makes no sense to try to correlate them. One of the things that keeps us correlating is there may be other variables that may be responsible for causing the correlation or non-correlation of my X and Y variables. We call those lurking variables. In our next segment, we will talk about how we develop this linear relationship between X and Y. How do we attempt to fit a line through our data in our scatter plot to determine the linear relationship between two variables?